In this lesson, we'll explore concavity, inflection points, and the second derivative test. So let's start off by talking about what is concavity. So a function is considered concave down, or sometimes just concave, if its second derivative, so the second derivative of the function, is less than 0. Technically, this is called strictly concave down. A function can be concave down if its second derivative is equal to 0, but we'll just talk about the extreme situation of the second derivative being specifically less than 0. Similarly, a function is called concave up. Some textbooks refer to this as convex. If its second derivative is greater than 0. So what's going on with these second derivatives? Well, just like the first derivative shows what's happening to the function, and when the first derivative is positive, the function is increasing. When the first derivative is negative, the function is decreasing. A similar thing is going to happen with concavity. When the second derivative is negative, that means the first derivative is decreasing. So when a function is concave down, this means that the first derivative is decreasing. And when a function is concave up, this means that the first derivative of the function is increasing. So what does that look like graphically? Well, let's start off looking at concave down. And let me just draw some arbitrary function here. And this function is going to be concave down, but let's see why. So this is x and this is y. And as we see, our function is positive over most of the part that I drew here, but more importantly, it is an increasing function, meaning that the first derivative is positive. So what do I mean by it being concave down? Well, the derivative is the slope of a tangent line at any point. So if we pick some pretty low x value, we see the slope is very positive. And if we pick an x value over here and draw a tangent line, the slope's still positive but less positive. And if we draw another tangent line over here, we see the slope is still positive, but again, substantially less positive. It's getting less and less steep. So the first derivative is still positive, but it's getting less positive, meaning that it's decreasing. So that's what the second derivative being negative is telling you. It's telling you that the slope, or the first derivative, is decreasing. And we call this concave down. Not all concave down functions look exactly like this. Sometimes if we have a decreasing function, it could be concave down like that, or it could be concave down like the way we drew, or it could be concave down making a complete downward parabola type shape. But as you can see, everywhere along this parabola, the slope is decreasing. It goes from positive to 0 to negative. So the slope is decreasing. Similarly, we can look at what concave up might look like. Okay, so let's draw a concave up function. And this function that I drew here does have a positive first derivative. But if we look, we pick a fairly low value of x, the slope is not that steep, and then it gets more steep and more steep, so it's getting more and more positive as x increases. So that means the first derivative is increasing, so it's greater than 0, which means the second derivative is positive, meaning the function is concave up. Concave up functions can look like the way we drew them, or they can be a decreasing function, but the slope is getting less and less negative, which is an increase in the slope. Or it can look sort of like an upward-facing parabola. But with the upward-facing parabola, as you can see, the slope starts off negative, gets less negative, goes to 0, gets positive, gets more positive. So the slope is increasing for concave up functions. All right, so moving on. Let's see how we can use this to find inflection inflection points and use something called the second derivative test. So let's start off with inflection points. An inflection point is just a point along a graph where the concavity changes, so where the second derivative goes from positive to negative or from negative to positive. So an example of this might be this curve right here. So I drew an arbitrary curve, but if we look to the left of this x value, you can see the function's concave down. It has that characteristic that the slope is decreasing as we increase in x. But when we go to the right of the x value, we see the slope is starting to increase, getting more and more positive. So the function's concave down over here and concave up over here, meaning the second derivative is negative on this part and positive over here. Now, one thing you may notice is that this graph does have some local or relative maxima and minima. There's a relative max over here and a relative min over here. And this is a trend that's actually going to be a consistent trend. Whenever we have a local maxima, the function's either going to be concave down or can't be determined. So maybe there's a sharp edge where we can't take the derivative. Similarly, whenever a function's concave up, there could be a minima. And there's never going to be a minima when the function's concave down. So concave down functions, we could have a local max. And concave up functions are good candidates for local min. Well, specifically over here. Local min would be over here. Local max would be at this point. Okay, so we can combine what we did for the first derivative test where we found the critical points, then plug those critical points into the second derivative of our function. And if the second derivative is positive, that means that our function is concave up, which means that critical point would be giving you a local minimum. And then if we plug it into the second derivative and we have a negative second derivative, that means that critical point would be a local maximum. So let's, finishing off with the inflection points before we get too far here. One thing about this inflection point is the concavity is changing there. So it's concave down to the left and concave up to the right. In order for concavity to change, so in other words, in order for the second derivative to go from negative to positive, it has to either go through 0 first or be undefined first. So to find inflection points, you're going to find the first derivative, second derivative, and then either set it to 0 or find where it's undefined. These are candidates. So these are candidates for inflection points. If the concavity changes on each side of that candidate for an inflection point, then it's inflection point. So for example, if at this value of x we found that the second derivative was equal to 0, then if it goes from positive to negative, or if it goes from negative to positive, then it's an inflection point. Otherwise, the test is inconclusive. All right. But before we get too far with inflection points, let's talk about the second derivative test for finding local extrema. So to do this, we're going to start off by finding our critical points, which means we set our first derivative equal to 0 or find where it's undefined. And those x values that we get from that are going to be our critical points. So we find our critical points using the first derivative. And again, we're going to either set this to be equal to 0 or find where it's undefined. It's going to be undefined wherever the denominator is equal to 0 if you're dealing with a rational function instead of a polynomial. Then you're going to take those critical points, we'll call them C, and plug them in to the second derivative. If the second derivative at any critical point is less than 0, that means the function's concave down there, which means that there would be a local max at that point. If the second derivative is greater than 0, that means the function's concave up at that critical point, which means there'd be a local minimum there. So the second derivative is quite a bit shorter than the first derivative, but it doesn't always work. Because if the second derivative at that critical point is equal to 0, which happens quite a lot, then the test is inconclusive. And if the test is inconclusive, oops, I'm misspelling that, inconclusive. If the test is inconclusive, go back to the first derivative test. All right, so let's try an example. Okay, so in this example, we're given this function, f of x equals x cubed minus 6x squared plus 9x plus 1. The question asks us to graph this function, find local extrema, and find the inflection points. So find extrema, inflection points, there may or may be more than one. And also to graph. Okay, let's start off by taking the first derivative, because the first derivative is what we're going to need to find inflection points and to find extrema. And we're going to start off by finding the critical point, so we'll find the extrema. So let's take the first derivative. So let's see, the derivative of x cubed is 3x squared minus 6 times the derivative of x squared, which would be 12x, plus 9. And then the derivative of 1 is 0, so we leave that off. So to find the critical points, we're going to set this first derivative equal to 0, or find where it's undefined. Since this is a polynomial function, it's not going to be undefined anywhere, so we just have to set it to 0. So we're going to set 3x squared minus 12x plus 9 equal to 0. We can do this by factoring, so let's pull out a 3. And we get x squared minus 4x plus 3 equals 0. Let's factor this. We get 3 times x minus 3 times x minus 1 equals 0. Set each of these factors to 0. Well, 3 is never 0, so I'll leave that one off. X minus 3 equals 0, or x minus 1 equals 0. Add 3 to both sides, we get x equals 3. Add 1 to both sides, we get x equals 1. So these are our critical points. Just for the sake of completeness, we can actually find the y values of these points by plugging them into the original function. And if we do that, f of 3, let's see, 3 cubed minus 6 times 3 squared plus 9 times 3 plus 1. I'll be honest with you, I used a calculator earlier and I found that this was 1. F of 1, if we plug 1 into the original function, we would get 5. And again, I did not do this in my head. I used a calculator earlier. So our critical points are 3, 1, and 1, 5. The reason why I wanted to find the y values of these points is because I know ultimately I'm going to want to graph these points. I'm just going to mark these off for later, and these are candidates for local max and local min, but I don't know which one's which. Maybe they're both maxima, maybe they're both minima. Maybe neither, maybe they're just false alarms. So we have to see. Okay, so to test, this is where the second derivative test comes from. We could do the first derivative test at this point by plotting them on a number line and picking test points. But let's use the second derivative test. So let's find the second derivative. So this was our first derivative. So let's take the derivative of that to find the second derivative, and we get 6x minus 12. Okay, so now we just want to plug in the x values, our critical points, into the second derivative to find which one's a max, which one's a min, maybe neither are. Let's figure it out. So if we find what the second derivative when x is 3 is, this would just be 6 times 3 minus 12. What's 18 minus 12, which is 6? And 6 is a positive number. Since our second derivative is positive at that x value, we know the function's concave up at that point. And if it's concave up, we know that there would be a minima, or a minimum over here. So this is a minimum. Okay, let's do the same for when x is 1. So we would get 6 times 1 minus 12. That's 6 minus 12, which is negative 6, which is negative, meaning our slope is decreasing, so our function's concave down. And if it's concave down, that means that's a candidate for a maximum. So this function here is a max. Not a candidate for it, is a max, I should say. So we've already found local high points and local low points of our function. We also want to find inflection points. To find an inflection point, we just have to find where the second derivative is equal to 0. So to find an inflection point, we just find where the second derivative is undefined or equal to 0. But again, since we're dealing with a polynomial function, it's not going to be undefined anywhere. So we just need to find where it's equal to 0. So let's set our second derivative equal to 0. So 6x minus 12 equals 0. Add 12 to both sides, divide by 6, we get x equals 2. If we plug x equaling 2 into our original function, and again, I did use a calculator earlier, and this gives me the point 2, 3. So 2, 3 is a candidate for an inflection point. We don't know it is an inflection point yet, but it's a candidate. So to find if it actually is an inflection point, we're going to mimic what we did with the first derivative test, but only with the second derivative. So our critical point here for an inflection point is 2. That's our candidate. And we just want to pick a number on either side of 2 and see what happens to the second derivative. We know the second derivative is 0 when x is 2. We want to find out what happens to the left and to the right of it. And if the sign changes, we know it's an inflection point because the concavity changes at that point. So let's see, pick a number less than 2, and any number over the interval negative infinity to 2 would work. So you could pick negative 1,000 if you like. But let's pick an easy number to work with. Let's pick a 0. And let's pick a number bigger than 2. Let's pick, I don't know, let's pick 5. That's pretty easy to work with. All right, so if we plug in 0 into our second derivative, so remember here was our second derivative. Let's see, 6 times 0 minus 12. That gives you negative 12, which is a negative number. Similarly, if we did 6 times 5 minus 12, that'd be 30 minus 12, which I think is 18, which is a positive number. So the concavity does change. Specifically, it goes from concave down to concave up. So this is an inflection point. So let's put all these facts together and graph this function. Okay, so I'm drawing my axes here. Let's see, some of the points that we want 3, 1, we want 1, 5, we want 2, 3. That's really it. Okay, so let's put all this together. So let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, I'm not drawing this perfectly. All right, you could probably draw this a little bit better with graph paper. All right, we know we have a minimum of our function at 3, 1. And we have a maximum of our function at 1, 5. And then we have an inflection point at 2, 3. So over here. So our function is concave down over here, concave up over here, and then there's an inflection point over here where the concavity changes at 2, 3. We also know that we can actually easily figure out our y-intercept if we go back to the original function. Remember, our original function was x cubed minus 6x squared plus 9x plus 1. Well, if we want to find the y-intercept, we just have to find what y is when x is 0. Well, when x is 0, we have 0 cubed minus 6 times 0 squared plus 9 times 0, so all that's 0 plus 1. So our y-intercept will be 1. We want to get a really good idea of what this function looks like. All right, so drawing our graph, we know the concavity has to change over here, so it goes from concave down to concave up, and then it loops around and goes up. And if you look, our function is concave down to the left of x equaling 2, and to the right of x being 2, it's concave up. So this is it. This is our function, and that completes this question.